everyone, my name is Beagon and I've prepared this presentation to cover the topic of contouring as part of our engineering surveying and levelling course here at DIT. As you move between each slide, the voiceover should come on automatically, but if you want to listen again, just double click the little speaker icon on the slide. Thanks. Just a reminder of the outline of the course. We covered surveying fundamentals, we did some work on linear surveying and carried out a practical for that. We talked about the different type of levels we have, and we have gone through in detail different levelling theory and calculation, including the rise and fall and the height collimation method. So we're now on the topic of contours, gradients and grids. This is the outline of today's lecture, an introduction into contouring, and I have a little quiz for you to do. Some of the characteristics of different types of contours, two methods of contouring that we'll go into in detail, and then how we interpolate contours once we have the information. How do we actually calculate what the contours look like? And finally, just some of the uses of contour plans, including how to draw a section. So the learning outcomes for this lesson. By the end of this lesson, you should be able to understand how to read a contour map, the two different methods of contouring a site and how to calculate them, how to interpolate level readings, so when you carry out spot levels on a site, how you're able to calculate where the contours appear and how to plot those contours on a grid, and finally how to draw vertical sections. So let's start with what contours are. A contour is a line on a map or a plan drawing which join points of the same height above or below a specified datum. In Ireland we typically use Malin Head, and you'll see on maps where it says MAOD, which is metres above ordnance datum. The contour is the line connecting the points of equal elevation above that datum point. So contours are shown so that the relief or the topography of an area can be interpreted. It shows where the hills and the valleys are. They can also be used to provide longitudinal and cross-sectional information, and that's really important if you're working on a scheme where you're either excavating or building an embankment. You need to know how much soil you need to import to the site or how much soil that you're going to have once you dig a trench. This is an extract of a topographical map with contours on it, and I just want you to take a minute to see what are you looking at. Hopefully you can see that we're looking at the top of a hill which has a summit elevation of 154 metres above ordnance datum, and you can see that the top of the hill is relatively flat, but once on the right hand side there you'll see 130, 120, 110, 100. Once we hit there, that's going down pretty steeply down the hill. Each contour on this map is at a 10-metre interval. On the left hand side of the map, hopefully you will also see that there's a valley which seems to have a stream in blue down it, and again you can see there how the valley is quite steep from that elevation of about 130. In the previous map we saw that the contours were spaced at 10 metres apart, and this difference in height is known as the contour interval or the vertical interval, and it dictates the accuracy to which the ground is represented. So if your contours are at 1 metre apart, it's going to be very, very accurate, but on those large topographical maps it tends to be at least 10 metres apart because you're looking for general information rather than specific information. Construction projects, you would probably need contour intervals of a metre, but as I said, 10 metres is fine for a topographical type survey on a map. So now we're going to look at some contour characteristics, and I want you to have a look at the 4 contours shown on this slide. Hopefully you'll see the difference between A and D is that the contours are very closely spaced in A but more spread out in C and D. And this indicates that the slope on diagram A is very steep compared to the slope on C and D, which is quite gentle. A contour which passes through any point is perpendicular to the line of the steepest slope at that point, and hopefully you'll be able to look into that in a bit more detail when I give you the contour quiz. This slide looks at the difference between contours on a valley, which is between two mountains, and a ridge line, which is sort of the edge or the backbone, I guess, of a hill. And how we signify both of these is either a U shape, which suggests it's a ridge line, or a V shape, which would suggest it's a valley. The contour maps on this slide show in diagram A a hill, which you'll see has a summit of about 115, and in diagram B a depression in the ground. So that might be something like a lake, let's say, where the bottom elevation of the lake is 85, and once you're coming out of the ground then at 95 and 100. So closed contour lines with ones inside it indicate a depression, but the easiest way to have a look at this is to identify where the highest level is and look at the contour levels on the sketch. A contour line must always close upon itself. That means it must form I was going to say circle, but a general outline and come back on itself, because really what that means, it says you're following the same level of ground around the site. Be careful though, that might not happen within either the limit of your site or the limit of the map. So when you're drawing it up, if it doesn't close in upon itself, that's not necessarily a mistake. Be very careful though, because two contour lines of different elevations cannot cross each other. They can become very close, which would suggest a very steep slope, but they cannot cross each other. And the reason that is if you had a contour of say 68 meters and a contour of 69 meters and they actually overlapped or crossed over each other, that would suggest that the piece of ground where that happens is both at a level of 68 and 69, which of course is impossible. However, if you look at the diagram on the bottom right, the top diagram is an elevation of a unusual looking mountain with a bit of an overhang on the left, and the bottom is a plan. So on the plan we're looking at the contours, and you can see there in dashed lines that indicates that that's the overhang. So in that particular instance, that's what that would look like. Okay, so here's a little bit of a contour quiz. You have two sets of diagrams here. One is a photographic diagram labelled A to M, and then a topographical map labelled 1 to 13. And you need to match up what topographical map matches the photograph. So just pause it here, take a few minutes and have a look to see if you can do that. Here are the answers. How did you do? For those that you didn't perhaps get completely correct, you might go back and have a look at the topographical map and the photograph and see if you can figure out why. There are two methods of contouring a site, and by that we mean by finding out the topography of a site by drawing a contour map. The first is direct, the second is indirect. So in the direct method, you are directly going on site and you are putting pegs in the ground to map out on the ground where the contours are. In the indirect method, that suggests you have a bit more work to do, and that's correct. The indirect method, you take spot levels on site and then you have to come back to the office and do some calculation to be able to draw the contours on the map. We're going to cover both of these in detail now. First, we're going to look at the direct method of contouring. Now, as I mentioned, in this method, the contour lines are physically followed on the ground. You do it directly on the ground. And it's really the opposite of ordinary levelling. So in levelling, what you're trying to find out is the level of a particular spot on the ground, something like 15.789 metres above ordnance datum. But in direct contouring, you do the opposite. You're trying to find the spot on the ground that matches a certain level you're looking for example 25.000 metres above ordnance datum, and that being your contour line, of course. In order to find the contour positions on the ground, you have to do two separate things. The first is vertical control, and that's about the elevation or the height above ordnance datum. Then the second step is horizontal control, and that's to enable you to draw a plan of the contours. The first step in the direct method of contouring is to set up your level and determine which contour line you want to look for. So in this instance, the level has been set up and a backside has been taken on to a temporary benchmark. Remember, with a temporary benchmark or an ordnance survey benchmark, you will always know that level. That's your reference point. And in this instance, it's 36.250. My backside is 1.630 meters, set on a peg at the TBM, and that enables me to work out my height of collimation, which is 37.880. Now, I know my height of collimation is at 37.880 and I'm trying to find the 37 meter contour line on the ground. So if you do a simple calculation with height of collimation, that would suggest that the reading on the staff would have to be 0.880 to determine that the piece of ground you are on at that point has a 37 meter contour or has an elevation of 37 meters. It has to be 0.880 below the height of collimation. So the surveyor on site will then have his assistant walk around with the staff while he looks through the level to determine which spots on the ground give a reading of 0.880. And they will put a peg in the ground at that point because they've just calculated that the soil or the ground at that point is effectively 37 meters above ordnance datum. So that's the first step, which is vertical control or elevation. They do this on a couple of points around the site. They try to follow the contour line around the site. Remember, we talked about how the contour line might try to close in on itself. So you do that within the confines of your site. And always remember, with the levelling, you always have to finish off back at a reference point to make sure you haven't miscalculated or misclosed your survey. So you'll see here the last reading they take is a foresight back onto the TBM to make sure there are no errors in the calculation. This slide shows two things. The top drawing is the vertical control or the elevation that we've just spoken about, and that is as if you're looking sideways on what's happening on site. The bottom diagram is the horizontal control. So this is, you're looking from above, you're looking down on plan, and each peg that you see there, peg A1, peg A2, peg A3 and so on, are the pegs that you see on the vertical control. So remember I said the surveyor kind of follows the contour line around the site. He's been putting in those pegs as he finds the reading of 0.880. Now, on site we now have several pegs in the ground that we know sit on the 37 metre contour, but we need to be able to record those to enable us to put those on plan. So similar to what we did on our linear survey or our booking sheets, you set out a traverse line or a baseline between two stations where you know you can plot those on a map, and then you simply book or measure at a right angle the distance along that line and the offset to each peg. And when you get back to the office, it means that you can draw the location of those pegs on plan, and of course then draw a line between them all, which indicates the 37 metre contour. So that's vertical control elevation, step 1, and step 2 is to measure where the pegs actually are on the ground, so you can put it on a drawing. In the direct method, remember we talked about directly on the site you would plot out the contours. So you literally put the pegs in to show where the contours are on the site. In the indirect method, you don't make any attempt to try to find out where the contours are on the site. What you do is you calculate a series of spot levels, so you just choose locations around the site, calculate the spot levels or the elevation of the ground at those points, and then when you come back to the office you interpolate between them. You work out using those spot levels where on plan or on your topographical survey the contours occur. Usually this is done either with identifiable locations like trees and gate posts, but in the situation that we have, we're going to set up a grid of 10 metres square, so it's 10 metres by 10 metres, along a baseline that we have on a map that we can reference from, and we're going to take spot levels in each one of those grid intersections. These are the three different steps in the indirect method. The first is to go out on site and create a grid with a baseline and pegs at regular intervals. So remember I talked about 10 by 10 metres in our particular scenario. Then you have to do a levelling survey and get the spot level of every one of those intersections. And finally, when you get back to the office, interpolate the contours, and you can do that either mathematically or graphically, and I'm going to show you both of those. This diagram or plan drawing shows how some surveyors have set out the grid. So you see they have a baseline line along the bottom between grid A1 and G1, And then they've offset at 10 meters a series of grids, and they've taken spot levels at each one of those intersections. I mentioned that you can interpolate between the grids either mathematically or graphically, but the first way you could do that is with estimation, just to estimate it. And with some skill and experience you can do this. It's not particularly accurate, so I wouldn't recommend it, but it is a good way to check what you've drawn, because you will know instinctively whether it's correct or not. So if we have a look at the diagram here on the screen, I want you to look particularly at the levels between 47.60, so that's 47.60 meters above ordnance datum, and 48.60. And if we look at the line between those two, it's clear that the contour of 48 meters, so say you're drawing contours at 1 meter centers, so I know that the contour of 48 meters passes somewhere between those two, because it's greater than 47.6 and it's less than 48.6. Now, by estimating that, I would perhaps consider that the contour passes that line at approximately halfway. So from 47.6 up to 48, I need to go 400. And from 48 to 48.6, I need to go 600. So they're not too far away. And that's why you'll see the person has drawn the contour line. It's approximately halfway between the two, although closer to 47.60. So that's with estimation. As I say, I wouldn't recommend it. It's just a good idea to check that you're not far off the mark. Now we're going to look at the second way of interpolating, which is the mathematical way, and this is the way that I'd like you to do it in any examination questions or for your practical. So the mathematical way is a very accurate way of interpolating, and I want you to have a look at point A1, which has a level of 67.70, and point B1, which is a level of 68.60. Now we can tell these are elevations, but we can tell that the difference between those two elevations is 0.9 meters. So going from A1 to B1, the ground rises 900 millimeters, or 0.9 meters. I can also tell by looking at that the contour of 68 meters passes between those 2 points, because we go from 67.7 up to 68.6. So 68 is in there somewhere. What I'm trying to do is to work out how long along that line, or how far along that line, does the 68 meter contour occur. Now, if I go back to the first suggestion I had in terms of estimation, by looking at that, I can tell that the line should be much closer to A than it should be, because it's only 300 mil to go from A1 up to 68 meters, and it's got 600 mil from B1. So in terms of elevation, I know I'm going to be closer to A1. When you're looking at the grid, it's important to determine what the length of the grid is. So remember I spoke about on site we will do a 10 meter by 10 meter grid when we go out to do the survey. But in this instance, the distance between A1 and B1 is 5 meters, and that's a planned distance, that's horizontally. So all we're looking at here is proportions. If the distance between A1 and B1 is 5 meters on plan, I need to calculate the distance to the 68 meter contour, and that is proportional to the difference in elevation between the 2 points. So I'm looking for 68, so 68.00 minus 67.70, which tells me proportionally how far I need to go to get to 68 meters, in this instance 0.3 meters, over the total elevation between A1 and B1, which is 0.9 meters, multiplied by 5 meters, my grid length, is 1.667 meters. So if I'm scaling this on plan, and the distance horizontally on plan between A1 and B1 is 5 meters, then I just scale along the line 1.667 meters, and I know that's where the contour of 68 meters passes that line. Now you will get some practice in doing this, but as I said, go back and instinctively think, I know roughly where this contour should go. It should be approximately third the way along that line, because I have a total elevation change of 900 mil, and I need an elevation change of 300 mil, or 0.3 meters, to get from 67.7 to 68. So it's effectively 0.3 over 0.9, or a third the length of the line. Now we're going to look at the second way of interpolating, which is the mathematical way, and this is the way that I'd like you to do it in any examination questions or for your practical. So the mathematical way is a very accurate way of interpolating, and I want you to have a look at point A1, which has a level of 67.70, and point B1, which is a level of 68.60. Now we can tell these are elevations, but we can tell that the difference between those two elevations is 0.9 meters. So going from A1 to B1, the ground rises 900 millimeters, or 0.9 meters. I can also tell by looking at that the contour of 68 meters passes between those 2 points, because we go from 67.7 up to 68.6. So 68 is in there somewhere. What I'm trying to do is to work out how long along that line, or how far along that line, does the 68 meter contour occur. Now, if I go back to the first suggestion I had in terms of estimation, by looking at that, I can tell that the line should be much closer to A than it should be, because it's only 300 mil to go from A1 up to 68 meters, and it's got 600 mil from B1. So in terms of elevation, I know I'm going to be closer to A1. When you're looking at the grid, it's important to determine what the length of the grid is. So remember I spoke about on site we will do a 10 meter by 10 meter grid when we go out to do the survey. But in this instance, the distance between A1 and B1 is 5 meters, and that's a planned distance, that's horizontally. So all we're looking at here is proportions. If the distance between A1 and B1 is 5 meters on plan, I need to calculate the distance to the 68 meter contour, and that is proportional to the difference in elevation between the 2 points. So I'm looking for 68, so 68.00 minus 67.70, which tells me proportionally how far I need to go to get to 68 meters, in this instance 0.3 meters, over the total elevation between A1 and B1, which is 0.9 meters, multiplied by 5 meters, my grade length, is 1.667 meters. So if I'm scaling this on plan and the distance horizontally on plan between A1 and B1 is 5 meters, then I just scale along the line 1.667 meters, and I know that's where the contour of 68 meters passes that line. Now you will get some practice in doing this, but as I said, go back and instinctively think, I know roughly where this contour should go. It should be approximately third the way along that line, because I have a total elevation change of 900 mil, and I need an elevation change of 300 mil, or 0.3 meters, to get from 67.7 to 68. So it's effectively 0.3 over 0.9, or a third the length of the line. The final way to interpolate contours is a graphical method, and this is pretty quick and accurate, but might take some time to get your head around. So on a piece of tracing paper, you draw lines at equal spacing, and every 10th line you draw in a solid line. So it's very clear that that's 0 to 10. Depending on the difference in elevation between contours, so it's difficult to see on the slide, but on the left here we have an elevation of 37.70, and on the right 38.6. So in this particular instance, the distance between the two in terms of height of elevation is also 0.9 meters. You then turn the tracing paper around so that the paper it cuts the line into 9 spaces. So remember, there's 0.9 meters of difference between these points. I've now cut it into 9 equal spaces. That's all the tracing paper does. It just cuts the line evenly. Out of those 0.9 spaces between the two points, I need to go up to 0.3 because I'm trying to find my 38 meter contour. So I just go along the lines 1, 2, 3, and that indicates to me along the line where the contour passes the line. So it might take you a minute to get your head around that. It's about proportioning the line. It's a similar scenario to the mathematical method. Once you have your contour map completed on plan, you may then be looking at uses for it, and one of the really useful things with a contour map is to draw a section drawing. So in construction work we often have to draw a section for a building or earthworks or excavations and so on, and a section is like a cut. So if you cut a slice through this cake that you see on the left, that's roughly what your section would look like. So if you come back to our contour map and you imagine the cake is a mountain, for example, then once we cut a section through it, we should see that the mountain rises and falls again. When we draw a contour section, we usually exaggerate the horizontal we usually exaggerate the vertical scale compared to the horizontal scale so that you can really see the difference in elevation. So typically a vertical scale is at 1 to 20 and the horizontal scale is at 1 to 200. This slide shows a typical contour plan. So hopefully if you were having trouble with the example on page 49, you can have a look at how this one was done. Remember, you start along the edge, you look to see if a contour passes the line, and then you just put a little line or a little X every time it crosses a grid line, and join them up, and that's your contour. Remember, once the contour enters a box, it has to leave the box, so be careful of that. What we're looking at here is both the plan, which is up at the top, and then section XX. So section XX, when we elevate that, we go from grid line 1A, 1B, 1C, 1D and 1E. The horizontal scale, as I said, is normally at 1 to 200 or to match your grid that you have the plan in. But you exaggerate the vertical scale. So here you can see the range of levels we have range from 25.2 at A1 up to 26.7 at D1. And all you do is you draw a vertical scale, in this instance from 25 to 27, and you plot at each point what the elevation of the ground is. And that's how you draw section XX on this contour plan. So in today's lecture we looked at an introduction to contouring, different contour characteristics, and you hopefully learned to read a few contour maps. And then the two methods of contouring, the direct method and the indirect method. And it's important that you're able to explain both of those and how you would carry them out on site. We then looked at the three ways of interpolating contours. The first by estimation, which whilst not recommended because it's not very accurate, it is a very good way of checking that the map that you've drawn is in the right realm. The second way is mathematically, and that's the way that I want you to do it within this course. And then finally the issue of the graphical way of doing contours, where you draw it on a tracing pad and do it graphically on a plan. And then we finished off just by how to draw sections using a contour map. The learning outcomes for this lesson were to enable you to be able to read a contour map, to describe the two methods of contouring a site, and particularly how you would do that on site, how to interpolate level readings on a grid, and how to draw the contours on a grid, which we've shown you an example of, and finally how to draw vertical and longitudinal sections from a contour map. So thanks for listening. I'll go back over any of the slides if there's anything you need to review.